Good evening and welcome to today's talk about Stardust. I would like to thank Dr. Rana Ezzedine for joining us today. Dr. Rana obtained her PhD in astrophysics from the University of Montpellier and did her postdoctoral research in MIT, which was focused on near-field cosmology, first stars, supernova, galaxies, early chemical enrichment, and earliest stars formation. She has also worked in the educational field in numerous schools and universities. Dr. Rana is currently working as an assistant professor and astrophysics researcher at the University of Florida. There will be a Q&A session after the talk, so if you have any questions, kindly leave them for the end. I will now mute myself and hand it over to Dr. Ezzedine. Enjoy.
Thank you, Sally. Hello, everyone. I'm very happy to be talking to you today. So as Sally mentioned, I'm an astrophysicist who's an assistant professor at the University of Florida. But I guess one thing worth mentioning before I start is that it gives me great pleasure to be talking to Lebanese university students because Lebanese University is my alma mater. It's where I did my undergraduate degree in physics, especially in the Hadath campus. And so it gives me really great pleasure to be back in, virtually and talk to you all about my journey so far in my research. So the title of my talk is going to be about Stardust, and this is part of my research. So what I would like to do in this talk is take you on a journey. I would like us all to embark on the journey across cosmic space and time to understand the chemical origins of the elements that constitute the world around us. In fact, and I would like you to tell me if you cannot see my next slide, but I hope that you do. Can everybody see my next slide?
Yes, we can.
Okay, perfect. Thank you. And so what you might or might not know is that we share a very deep connection to the stars. In fact, all of the world around us is made of dust and elements that have been formed either at the core or via the stars. Our bodies are made of oxygen, carbon, other elements that have been forged at the cores of the stars billions of years ago and have made their cosmic journey across what we call the chemical evolution of the universe until present day. Or not even the present day, until when our star, the sun, was formed from these chemical elements and the planets around it, including Earth. And so it is very natural for us to ask questions about the origins of these chemical elements. I might be interested, and you might be interested to know where the oxygen on your blood came from. Where did the carbon come from? Do we have any parts of the Big Bang, or do we have any constituents of the supernova explosions that happened billions of years ago in our blood in the present day? To give you the short answer, this is yes. We are actively made up of elements that have been exploded through lots of interesting events throughout the universe, and these elements have made their way to the present day. And I hope in my presentation today, in my talk, to tell you a little more about this. And in the occasion of chemical elements and talking about the chemical elements, I would like to highlight that 2019 was the 150th anniversary of the periodic table. This is a table that you've all, I'm sure, stared at and know very dearly. It was written, or it was created by Mendeleev, who attempted to try to put all the elements together in a format that allows us to understand the connection between them and how we get to understand them from an atomic and a nuclear point of view, pardon me. But you'll be interested to know that while we know where most of these elements came from in the periodic table, we still have a lot of standing questions. And in my research, I aim to answer some of these questions, particularly the origin of the elements that lie in the bottom half of the periodic table. And you see these are elements that are heavier than iron that are shown here. the origin of these elements, what we call the heavy elements, have been elusive for a very long time. And in 2017, the universe gave us a beautiful gift. And this gift allowed us to have an insight into the origin of these chemical elements. And I will talk about what this cosmic discovery was just a few years ago. So to tell you that the conquest or the enquest to try to understand the chemical elements is still ongoing until the present day. And so to give us to get us all in the same thinking space, we should go all the way back to the very beginning, which is all the way to the Big Bang. As you know, the Big Bang was the start of everything, the start of the universe. But what did the universe look like a few minutes after the Big Bang? It was mainly empty, and the universe was only made of hydrogen and helium. No chemical elements were present in the ISM or the interstellar medium at the time. Maybe a little bit of lithium and beryllium, but not much else. A few million years afterwards, or 100 million years after the Big Bang, the very first stars in the universe were formed. These stars were the cores at which the very first elements that are heavier than hydrogen and helium were formed in the universe, particularly elements such as carbon and oxygen and iron. This is where they got forged for the first time in the first stars. Anything heavier than that came after the first stars onward. However, we have a dilemma here. We cannot observe the first stars. They are no longer around. They are very old. They were very massive, and so they must have exploded by now. And so how do we get around understanding the formation of the very first elements in the first stars if we can't observe them? We have to go around this and try to study the best next thing, which is the second generation of stars. And these are the stars that came from the chemical elements that were enriched by the very first stars. So they are kind of their children. And interestingly, as I said, we cannot observe the first stars. In fact, we cannot observe directly in the universe anything that is below or beyond 1 billion years. This is a very opaque part of the universe for us. However, we study it in different ways. We aim to simulate it with our cosmological simulations by putting what we think was the eluding physics or the important physics taking place at that time. So as I said, the universe was made only from hydrogen and helium. And of course, there was, the physical forces between the elements, these atoms, and also dark matter. And so here I'm going to show you a video of the actual play, of a beautiful play, a theatrical play of how the universe got to come together to form the very first galaxies in the universe and the very first stars. And what you are seeing here is the time going forward all the way from the Big Bang and from this universe that was made only from hydrogen, helium, and dark matter, where, of course, due to gravity, things started collapsing and forming the very first galaxies. And you can see here we are looking onward in time. So the time is decreasing, but in fact, it's actually just moving forward until the present day. So the galaxy that's being formed here, this is a Milky Way-like galaxy. So it looks very much like our own galaxy. And so you can see that it was formed from the infall of lots of matter that we call mini halos. And so these mini halos were the sites at which the oldest stars in the universe were formed. And then they collapsed together to form the present day galaxies. And this is an acceptable or a very widely common formation scenario for our galaxies that is widely accepted in the astronomical society. And so once we understand the formation of the stars, now we want to go back to our question of how did the rest of the chemical elements form, or how do we get about trying to understand a topic like this? In order to do that, we need two parts, or we need to understand two physical processes. One, which is nuclear physics, and which tells us how the elements formed. So we need to know how do the elements form, what kind of energies do they need, what kind of environments do they need. And usually this tells us how the light elements, so anything that's light, meaning that it's less than iron in the periodic table, and it tells us how the heavy elements form. And the other part that we need to also know about and understand is the astrophysical side. And so knowing how the elements form, both light and heavy, how do we put this in an astrophysical concept or in an astrophysical point of view in order to understand it? In astrophysics, we need to know about the chemical evolution. So how did the chemistry across cosmic time evolve? And we need to know about stellar archaeology. And I'm going to explain this to you, what exactly it means. But let's start with the nuclear astrophysics part. In order for us to understand the evolution and the formation of the chemical elements, we need to know how they form. As you may or may not know, the heavy elements, or the elements that are up to iron, are usually fused at the cores of the stars. But we usually have two types of stars. The universe creates massive stars, which usually end their lives in very energetic supernova explosions called type 2 supernova explosions. And these usually emit at the end of their lives the light elements such as magnesium, silicon, sulfur, etc. And the other type of stars that we know are the low mass stars. These low mass stars don't eject as much elements, don't end their lives in such type supernova, but rather when they are in a binary system along another star, they usually, at the end of their lives, they have a special relation where they kind of make a connection where a lot of the elements from one of the star gets accreted onto the other type of star, or on the low mass star, which is called a white dwarf. And this ends up with another type of explosion called type 1a supernova. And type 1a supernova is usually the dominant side for the production of iron in the universe. And so as we know now that massive stars are responsible for the formation of heavy elements up until iron, type 1a supernova is responsible for everything that is around iron, which we call the iron peak elements. We can progress forward in order to understand how these come together in our understanding of the evolution of the chemical elements. And so here, just to show you this in more details in a little simulation or in a little cartoonish GIF, so you can see that the elements up until iron are usually forged at the center of the star by nuclear fusion, where two elements or two atoms come together to form heavier and heavier elements. And this is quite understood. Now, the other question is, how do elements that are heavier than iron form in the universe? Is there another process? Because stars cannot form elements that are heavier than iron. This is actually the top at which the energy which is produced by stars is able to produce chemical elements. So what about other elements? Let's say gold, let's say uranium. How do these form? These are formed by a different process called the neutron capture process. And as you can imagine, it requires a lot of neutrons. And so we have usually two sites for this neutron capture, one which is called the slow neutron capture. So it requires a small flux of neutrons bombarding our atom and forming heavier elements. And another is called rapid neutron capture, where a huge flux of neutrons bombard the seed atom and form heavier elements. We know a lot about the slow neutron capture process. We know that it happens in evolved stars, but we don't know a lot about the rapid neutron capture. In fact, where can we find an environment in the universe that has such a huge flux of neutrons bombarding an atom to form heavier and heavier elements? As you can imagine, we probably need to look at somewhere that's really explosive and has a lot of energy in it. And we will see later what that is. So before we go to that, I want to get you back onto the stellar astrophysics thinking space. So we said that the chemical elements are formed inside or via the stars. And so far, we've looked on the nuclear astrophysics part, which is where the elements forge and the process by which they are formed. But does stellar astrophysics help us to pin down the origin of the chemical element? As you can imagine, of course it does. One of the premise of my research and that of my colleagues is understanding how the chemical evolution of the universe proceeded since the Big Bang until the present day. So what you are seeing here is a kind of a cartoon that shows you that at the beginning of time, so since the Big Bang, so here we are looking at the very beginning of the day. As I said, the universe didn't have a lot of elements in it. It was mainly hydrogen and helium. When the first stars came to be, they ejected, or when they exploded, they ejected the first heavy elements into the universe. And so this proceeded, and then these elements moved into the second generation of stars, which had a little more heavy elements than the first stars. The third generation has a little bit more, the fourth, etc. So as we move forward in time, the universe gets enriched more and more with elements. And so this means that if I study a star that is very, very old, it should not have a lot of elements in it, because at the time, the universe didn't have a lot of time to make this. If I study a younger star, like our sun, I would see that it has a lot of heavy elements in it because it's a young star. And so we use this criteria in order to try to understand how the chemical elements formed. And when we study the stars at different epochs, we can understand the chemical evolution. And so, as I said, this chemical evolution comes from the premise that stars are naturally evolving. They are not static. They don't stay around forever. When they end their lives, they eject all the material inside of them, if they explode with supernova explosions, into the interstellar medium, from which new stars are formed, from which new planets such as our Earth is formed, and so forth. And you can see that this is a very iterative method, continuing on all the way since 13 billion years ago. So again, the very young stars have the early stars have a little bit of elements, the younger star have a lot. And this is an important point to remember, because we're going to use that to understand, or to put ourselves into the space of how, or which type of stars do we use to understand the chemical elements. And so going back to the periodic table, as I said, we need to classify our stars as old and young. But is there an indicator in the star that tells us which is old and which is young? Because when we look in our telescopes, we see the stars looking all the same. You know, that only depends on how far we're looking or how bright a star is. So how can we tell if it's young or if it's old? Going back to the periodic table, astronomers decided to change the format and basically assume that anything that is not hydrogen and helium to be called metals. And so going back to the concept that old stars should have very little elements, we call them metal poor stars. So metal poor stars are simply stars that are just very old and did not have time to have a lot of metals in them. And of course, by metals here, we mean all the elements, magnesium, iron, that are not hydrogen, helium. Whereas younger stars, we call them metal rich. Okay, so it's just an indicator of how old a star is by studying the metals in them, or the chemical compositions of metals. And once we know this, we can now, or you now are probably forming the concept that for us to go back and study the formation of the chemical elements, we probably need to study old stars. Why? Because old stars were formed from pristine gas that has not been polluted by a lot of events. And so if we go back there, we can isolate a certain set of stars that allow us to probe directly the type of chemical enrichment that could have taken place in the early universe. And this is the type of stars that I study. I study stars that are metal poor, that are very old in the universe, and I use telescopes to identify them. I will show you in a minute how I do this. And then I apply the concept of stellar archaeology. So archaeology, you might be very familiar with, right? It's digging for old fossils underneath the ground. And then once we have these fossils, we try to make a connection to the history of this region where we found the fossil. And so we do the same with stars. We look for these low mass old stars in our Milky Way galaxy, and then we use their chemical compositions to trace back the origin star-forming cloud from which they were formed, which tells us a lot about the origin of the chemical elements. And so, as I said, there's an analogy there. On Earth, we look for stellar fossils in order to understand its history. In stellar archaeology, we search the Milky Way for the oldest stars in order to understand its history. And so how do we go about doing this? Or how do we identify these stars? As I said, the universe, and particularly the Milky Way, is full of stars. Is there a particular place we can look to find these stars? We usually go through multiple vetting processes, and we know that the majority of old stars are found in what we call the halo of the Milky Way, which I like to call the junkyard of the Milky Way. It's basically the oldest part of the galaxy, and it's not like, so you know, the galaxy has the disk, which is relatively young, and then everything else is found around this disk in what we call the halo. And once we've identified suitable targets, we go to our biggest telescopes because we need really high resolution, and we try to collect the spectra of these stars. We also sometimes use space telescopes such as Hubble in order to understand or try to collect as much information as we can about these stars by studying their full chemical composition abundances. And so when we go to the telescope, what do we collect? We collect a spectrum. Some of you may be familiar with the word spectrum, and some of you may not. I thought I would just kind of explain it briefly. So if an alien world out there happens to be lucky enough to point their telescopes toward our sun, what would they see? They would see a spectrum of the sun, or the sun's rainbow. And in this rainbow, they will see these dark patches of light or non-light. It means that light has been absorbed. Interestingly, it has been shown by many wonderful women such as Annie Jump Cannon, Cecilia Payne, and others, that every one of those dark patches correspond to a chemical element that we know very well exists along where the position of this dark patch should be. And using this concept, which is basically just a prism concept, if you were to bring a prism, look into the sun, and then put some kind of gas in front of it, whatever the gas is made of, whatever atoms it's made of, whether it's hydrogen, argon, whatever it is going to absorb part of this light that's coming from the sun, and we see it in the spectrum. And then we convert it into what you see here below, which is a spectrum of the sun showing iron elements, showing sodium, showing hydrogen, etc. And so this is a really great thing, because now when we go to our telescopes, collect the spectrum of light of the star, we can study its composition. And what we see is that these lines, so the dispatches correspond into these lines, or these absorption lines that are at specific wavelengths. And we measure the absorption lines, we measure the area underneath each of them, which tells us how much of these chemical elements are found in the stars. What you are seeing here are 4 different spectra of 4 different stars at different ages. As you can imagine, the one on the top is the youngest star because it's a lot metal rich. Look how many lines it has. It means there's a lot of atoms inside the atmosphere of this star. But as we go below in the spectra, we have less and less lines. This means that we are now studying older and older stars because the lines go away, which means we don't have a lot of these elements found in these stars. And so when I'm looking for the old stars, I look for the stars that have the least amount of lines in them, or the least amount of these absorption lines in them, because this means I found my oldest stars. So this is the vetting process that we usually do when we are looking for the oldest stars. Now, I've explained to you how the elements formed, how do they get their way into evolving from the old stars to the present day stars, what kind of stars I'm interested in to study. And the answer, of course, is old stars or metal-poor stars. Now I would like to give you a little bit more insight into my research, particularly looking for the origin of gold and uranium, which, if you know your periodic table, you would know that it's at the bottom part of the periodic table. And so knowing this knowledge that I just kind of walked you through, I'm going to use the same techniques to tell you how I look for the origins of gold and uranium in the oldest stars in the universe. And by that, I promised you I would tell you of a really cool event that happened in 2017 that broadened our perspective and allowed us for the first time to know how these elements formed. So again, going back to the periodic table, as I said, the lower part of this periodic table here is still unknown. The origins or the sites of formation of these elements are still unknown. And I alluded earlier to a process called the R process, if you remember, which stands for the rapid neutron capture process. So just to remind you again, this is usually the formation of chemical elements by bombardment of a seed nucleus with a lot of neutrons, and the element grows bigger and bigger and bigger. And then when it does that, it forms heavier elements. These elements are usually unstable, and so they are radioactive, and so they beta decay until they form more stable elements. But they basically are responsible for the formation of all the elements, including gold and uranium. And so up until 2017, astronomers were very puzzled about the origin or where would such an R process take place. As you can imagine, you need a huge flux of neutrons. And so where in the universe would we find so much neutrons? One idea is neutron stars, right? I mean, these are stars fully made of neutrons. But would one star be able to actually give us the flux? What if we get two neutron stars and kind of bombard them together or get them to merge together and explode? Then you would get a lot of neutrons, right? Because then a lot of this flux is just going to get out of this merger event. And the first thing that was very promising in the search of the sites of the R process was before 2017, was in 2016, when LIGO and Virgo detected the very first gravitational wave. So many of you may be not familiar with the term gravitational wave. This is just a space-time continuum shift when two very heavy objects, such as black holes or neutron stars, merge together. They would create literally a dent in space-time that would then create waves, and we will be able to detect them, or LIGO was able to detect it in 2016 as was predicted by Einstein. So that was very cool. And then in 2017, we were able to, or LIGO was able to collect the very first gravitational wave, not from two black holes, but from two neutron star mergers. Of course, scientists and astronomers have postulated and knew that these events exist in the universe, but we've never been able to actually observe one. And so the gravitational wave detected from two neutron star mergers triggered all astronomers to point all their telescopes toward this event. What we saw was this amazing, of course, gravitational wave signal. But then what happened is that the telescopes, which are usually here on Earth, they don't detect gravitational waves. They detect light, right? And so when we pointed our stars, our telescopes, we were able to collect the light coming from this event of two neutron star mergers. This event is called a kilonova. A kilonova, you might be familiar with supernova, but maybe not kilonova. Kilonova is just a smaller energy supernova. And the kilonova usually comes from the neutron star mergers. And what you can see here on the y-axis is the flux of the light, so the intensity of the light as a function of wavelengths. You see that there's multiple colors. And these colors denote of different regions in the light that we have actually been able to collect it. Part of it was blue or toward bluer colors, and this was very short. And the other part was red, which lasted several days. So as long as the telescopes were observing, they kept collecting light. So what is the significance of this kilonova? In fact, a kilonova is an event that is due to or is powered by the radioactive decay of R process elements. So lots of R process was being formed in this neutron star merger, just like astronomers had predicted. And so this was conclusively, or we were able to conclude that the R process, the main or dominant side of the R process, is a neutron star merger accompanied by a gravitational wave. How cool is that? And so interestingly, though, the media at the time reported that astronomers struck gold. We were able to find all the gold in the universe in neutron star mergers. I'm sure you must have heard about it somewhere. It's like, finally, the astronomers brought all the gold they were promising us. That was a little bit of a misnomer, though, because we didn't detect gold directly in that event. In fact, we cannot do it, because imagine when you have two neutron stars merging, they're going to eject a lot of material that's going to be moving at a really fast pace. And so any absorption lines that you would look into that, they're going to be blurred. You're not going to be able to see them. But we can study the R process, or we can study the formation of the R process, again, going back to the oldest stars. Why? Because any neutron star merger that happened in the early universe is going to have its imprint on the spectra of these very old stars. And in fact, we find them. When we look, as I said, when we vet our Milky Way halo and we try to look for stars, sometimes we find those that have so much R process in them, like the spectrum of this star here in red. This is HE 1523-0901, just a phone number, but it's a very interesting star because it was one of the first stars that showed we have so much R process in it. Look at Lanthanum, Sumerium, Dysprosium. You might not be familiar with these names at the bottom of the periodic table, but I've learned to memorize them because I study them a lot. But that was very interesting because we can find the imprint of an event that happened 13 billion years ago on our stars. And so because of this really cool event, my colleagues and I have started a collaboration called the R Process Alliance, which is, as cool as it sounds. We're basically a collaboration trying to point our telescopes into the old part of the Milky Way to try to find as much stars, old stars particularly, that have a lot of gold in them, a lot of our process elements, and try to trace this back to understand how these elements form. And so we are currently, this is work in progress. We have already put several catalogs out there for about 100 stars that are highly enhanced in the R process, and we're working on more to try to answer this question. Another thing is that the interesting part about our process stars is that we don't only find them in the halo. So remember when we talked about the halo, so this is the galaxy, this is the galactic disk, and this is the halo here, or the junkyard. But in the galactic halo, we also have other systems or satellites that surround our galaxy. This is what we call dwarf galaxies. These dwarf galaxies are believed to be the remnants of the first galaxies. So they are, remember the video that we watched at the beginning of this talk, which was forming the Milky Way? These tiny little yellow particles. It is believed that these dwarf galaxies are really the remnants of these halos that formed the very first galaxies in our universe and our Milky Way. And so they are very old systems. And sometimes when we point our telescopes toward them, we find that they have really nice R process stars in them. So maybe there's a connection. Maybe by studying the R process stars in these galaxies, we can understand the formation of our Milky Way. We can build this connection together just by studying the chemical compositions of stars, understanding nuclear physics, and studying stellar astrophysics, which is really cool because it brings all the picture together. Finally, I'm super excited about the future, the current large telescopes and the future large telescopes coming into our community, because right now we are hindered by the small, well, they're big, but still they're relatively small telescopes. We cannot go as far outward into our galaxy as much as we like. As I said, the old stars that we're interested in, that tell us where the elements form, are very far in our Milky Way and are very faint. And so we need bigger and bigger telescopes in order to understand them and study them. And so there's a future set of telescopes like the Giant Magellan Telescope, the 30-meter telescope, and others that are coming into construction in the next few years. These are going to allow us to go even farther to study stars much broader than that and help us continue to understand the formation of the chemical elements and the structure of our Milky Way. I'm going to stop here. I hope that you have learned and you have enjoyed this journey with me across cosmic time to learn about the origins of the chemical elements and to really find this connection with the stars. I certainly feel it very strongly. We are part of the stars and we really find these elements in our bodies until the present day. And in the light of the events that are happening this week, the World Space Week, particularly celebrating women in space, I would like to ask you all to please keep supporting women in science, because there is no reason why science should be gender biased. We are all capable of doing great science, and so are you. And so if you look around yourself in a classroom and you can't find someone who represents you or looks like you in terms of going into science, maybe go and look somewhere else, or go online, go on Twitter, or even talk to me if you like, because there's a lot of women in science. And as you saw with Cecilia Payne and others, we've been doing a lot of really interesting research all along. So I will stop here and take any questions.
Thank you, Dr. Rana, for sharing your journey with us. I have already posted in the comment if anybody has any kind of questions for Dr. Rana. Okay, there's somebody is asking about your email, because we just asked them to contact
Of course,
you.
yeah, I will post it in the comments. I see Jean-Pierre has a question.
Let's see. Yes, Jean-Pierre is raising his hand. So
Yes, hello. Long
Hello.
time no see. It was great. This is great to receive you, especially that we are celebrating women in this World Space Week, and we are celebrating women in space. So you are our ambassador to space also. So it was great, really, to listen to you now, and really very interesting as usual. We thank you a lot, and we are so proud to have Lebanese women, Lebanese ladies reaching this level of science, and we are looking forward to see your achievements in the next years, and wishing you always good luck. So I don't have any question, but I just wanted to say this, and thank you a lot.
That's very kind of you, Jean-Pierre. Thank you.
Thank
I'm
you.
always happy to be here and talk to Lebanese youth and Lebanese space enthusiasts, because I'm very happy that finally we have space events going on in Lebanon. And when things are a little bit hard, I guess, life-wise right now, I just want us to keep dreaming, because this is really what we need to do. So I'm always happy to be here. Thank you, Jean-Pierre. I know sometimes it's a little bit, sometimes we're not sure about our question, or we may think that we don't have a good question. So I would really encourage any types of questions, even if it's not related to the talk. I'm always happy to answer any questions you have.
yes, we can still wait for more questions. Okay, we have a question from Hassan Musa. So can we suppose that time doesn't exist because before the Big Bang because of infinite density and gravity? It's slightly out of topic, but of course we can discuss it.
Yeah, I can attempt to discuss it at least. Thank you for your question. So I am not a cosmologist. However, I'm sure that as any astronomer or astronomy enthusiast, we've thought about this point, or we thought about this question is, how can we really understand what happened before the Big Bang? As far as we can tell right now, and based on cosmology simulations and also cosmological observations of the cosmic microwave background, etc., there's a lot of indications that space, of course, didn't exist before the Big Bang. Now, in terms of time, I usually correlate these two parameters together. I find it hard, at least in my brain, to disentangle them because, like you saw, in order to understand the chemical evolution, we need to have a certain reference. We need to have an axis of where time and space started and how it evolved over time. And so this is why, for me at least, I think that these two are highly correlated. Now, whether time existed before that, in terms of parallel universes, I'm afraid I'm not the expert on this, but I think that I don't think about these things in terms of time. I think that time started after the Big Bang or at the moment of the Big Bang. I hope that answered your question.
Thank you. And we also have another question from Layla Al-Hanni. I'm wondering if the gravitational waves had sounds, maybe?
Yeah, actually, that's a really good question. That is true. It has a sound, and maybe I'll try to find it and make you guys hear it. It's a very little chirp, and this chirp is because of this dilation in space and time. It was more like a boop. It was very, 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 very fast because the time scale of a gravitational wave actually happening is very short. And if you go on the LIGO website and on the Virgo website, they show the different sounds that they've collected from different gravitational waves detected by LIGO since 2016 until today. But of course, the neutron star merger itself also had a small sound. I think the strongest was probably the first black hole merger in 2016, which has a very cute little kind of chirp that happened. And so, yeah, they do have sounds, but that's a very smart way to think about it.
Thank you. Waiting for more questions.
I think Mark had his hand up earlier.
Let's see.
Yes, hello. I just wanted to thank you أول شيء عن جد thank you دكتور ومثل ما قال جان بيير إن إحنا we're so proud أكيد إنه في أشخاص مثلك بيمثلوا لبنان. بس عندي small question about هلا نحن بنعرف أكيد البروسيسز وقت نحكي stellar physics يعني stellar astrophysics وقت نحكي كمان الelements الفورميشن الفيوجن كله أكيد في long processes وكتير طوال ومعقول يكونوا أوقات كتير صعبين. Do you recommend طريقة معينة نبلش يمكن نفهم شوي مثل ما قلتي أوقات التيبل مش معودين نوصلها للآخر. We're not used to learn all the elements يعني بالأول يمكن نكون أول 20 elements. So ما بعرف do you recommend طريقة بس حتى نفوت شوي بالنيوكلير physics والنيوكلير synthesis شوي يمكن at least ناخد فكرة detailed أو what are the references يمكن at least simple وهي one of the best ideas يعني دايما وقتها when we start to learn this with my students بقول لهم إنه هيدا أجمل lesson the best lesson يمكن science بتقلنا we are made of stars. So thank you a lot.
Yeah, of course. So when I started learning about the elements, I remember I was actually doing my master's at Notre Dame with Dr. Marwan Gibran, and that was the class I was taking. And over Christmas break, he gave us a paper to read, and it was the longest paper I have ever read. It was about 180 pages long, and this was written by Burbage, Foiler, and Hall. It's called the B2FH paper because of their names. So Burbage is, the first Burbage is, by the way, a woman also. She wrote this paper back in the 50s describing in details how every single element is formed, and so the process by which every single element is formed. And of course, as you can imagine, it's not a light paper, like you're saying. It's not easy. It's complicated because it goes into a lot of details, but I think it's definitely worth checking at least. Since then, and by the way, she did also talk about neutron star mergers as possible, or neutron stars at least, as possible sites for the R process, so all the way back in the 50s when we had never observed it. And so this is one way to start. Of course, over the years and now with the interest of astronomers in nuclear astrophysics and trying to understand the chemical elements, there's a lot of research out there that's much more simplified. And so you have a lot of review papers that are much more, let's say, friendly written that you can find, and I'm happy to refer you to some of these. You can also look at some websites of collaborations that are interested in nuclear astrophysics. So I am part of a collaboration called GINA, which is Joint Institute for Nuclear Astrophysics, and all the astronomers there are interested to answer questions about the elements. And so there's a lot of very brief, brief overviews of how the elements formed. And finally, if that's not all enough, of course, it would be nice to have this origin of the chemical elements as an outreach, right? We want to bring it closer to people. Like you said, people rarely think about the lower part of the periodic table. I only started thinking about it a few years ago, to be honest, but now I just love it. It's beautiful. There's so much diversity. And so I'm very interested actually to start an outreach project which would bring highlight to this. So one idea I have is to start an online website called the Atom Hotel, where you have the periodic table is like a hotel, and every room or every element is a room that when you click on it, it tells you about this element. And if you're interested in something like this, I'm more than happy to talk to you about it and collaborate even with you and others to creating this website to kind of bring it closer to people.
Thank you a lot, really amazing.
Thank you.
Dr. Rana, I do have a question. Probably it's also unrelated, but it's going to be a continuity for your answer for Hussam Musa, because you just mentioned that will be the topic of cosmology, not the topic of astrophysics or the topics you're doing. Maybe not many people know about it in here, maybe about the difference between the cosmology and the astrophysics in general, maybe a small differentiation between both topics in here can be helpful.
Yeah, of course, yeah. Thank you for bringing that to my attention. I guess I didn't put one and one together. So astrophysics, the definition of it is obviously studying the physics of astronomical objects, right? And trying to understand the way they behave. Most of the time, we spend our times studying their light. And I think light might be one of the main differentiations between cosmology and astrophysics. In fact, we cannot really put them fully apart, because when we study astrophysical objects, we have to put them in the bigger context of how do they all connect to each other? How do they all connect to the universe around us? And is there a bigger picture that we're not seeing? And so this is what cosmology is. Cosmology is kind of taking a step back, a really far step back, and trying to understand the constituents of the universe from the point of view of looking outward in time and thinking about the big questions of how did the universe come to be? How does looking at the universe as one object, so looking at all the stars or the galaxies as a single object and studying its light, but of course there's no light, but there's cosmic microwave background, which is the only light that is remaining dating from the beginning of universe. And so there's some people studying that and trying to understand what these tiny little structures tell us about the universe as a whole. And so when I study chemical elements, I'm going really deep into a very detailed topic here, which is going all the way into stars, understanding how they form these elements. And as you see, I cannot only use atomic physics, but I also have to take a step back and study stellar astrophysics. For cosmology, they take a much bigger step back. They ignore all the constituents of this universe. They don't really study the stars or the galaxies, but they take a much further step back in order to understand space, time, and the origin of the universe itself. I hope that's clearer.
Pretty clear. We do still have two questions from the comments actually. Hello, I have a question. What is the chemical composition of dark matter? It's a very nice question.
Yeah, very nice question indeed. So I guess to give you a feedback before answering this is you have to know that everything that we collect light from, or all the elements or the matter, we call them baryons, they really constitute nothing but, I would say, 5% or even less of the universe. The universe is mainly composed of what we call dark matter and dark energy. And dark matter, as you can tell from the name, it's dark. So we just cannot see it. It does not emit light. But it's an interacting particle, meaning that it's a particle that interacts with matter and with light, but has no mass. So as if it's really like a massless chemical element, or not chemical element, it's a massless particle. And so until present day, as far as I know, there's been many candidates for what this dark matter could be. Some people have suggested different particles, and this is the work of people working at CERN and other places to try to confirm what kind of dark matter we have, how does it interact. But it's not really an element in the conventional sense of elements like we know them, like hydrogen and helium. For hydrogen and helium and other atoms, we know that they have a nucleus, which has protons and neutrons, and we know that they have electrons around them. This is something we know a lot. For dark matter, because we don't know the nature of it, we don't know what it's made of. We only know how it interacts with the medium around it because we have been able to get some hints from our studies of the effect of dark matter on astronomy, but we haven't been able to really pin down and say, okay, this is what dark matter is. So unfortunately, until the present day, we don't know what its chemical composition is or even what it is. It's still a mystery. And if you're interested in astronomy or studying astronomy, I would recommend you, maybe going into that field and trying to help astronomers figure out what dark matter is. But yeah, really good question.
What a great motivation. We still have the last question here. Hi, Doctor. Do you think that Lucy mission of the 7 Trojans asteroid will help us to discover a new elements?
Yeah, that's a good question. So I think that so first of all, let's think of what asteroids are, right? So asteroids are these particles or these kind of rocks that are the remaining of the formation of our solar system. So our solar system, as you know, at the center is a sun, and all the planets around it have been formed around the sun. And so anything that wasn't dense enough to form a planet formed these, asteroids, such as the asteroid belt. And so based on our knowledge of the formation of stars, we can tell that the asteroids should not be composed from chemical elements that we don't know, because they should have the same, because they were born from the same cloud, they should have the same chemical compositions as our sun, as our planets, as Earth, right? And so we always try to answer these questions based on previous knowledge. And up until now, with the knowledge that we have, we doubt that we can discover, or that we possibly going to be discovering a new element on asteroids. However, we might be able to discover new molecules because the conditions on asteroids are different than here on Earth. And that's still invaluable because it allows us to also learn about the chemistry of these types of objects. But I would not say that it's a new element. So I hope that was clear.
That was definitely clear, and still really the last question in here before closing, because after we're gonna take 5 minutes break for the next talk. This is from Zoshama. Hi Rana, concluding question. As the main theme in Women in Space, how do you think the increasing interest in women and girls in becoming pioneers, like yourself, you would make an impact in society? Thank you.
Yeah, thank you, Joe. It's nice to hear from you again and see you again. This is a very important question, and I'm glad that we are kind of wrapping up with this. I think that it's very important of the inclusion of women and becoming more involved in STEM fields in general, but particularly in astronomy or in space sciences, simply because any gender bias that is based on science, based on education, is not a healthy description, or it's not even a healthy reflection of a society. We are here, right? We are 50% of genders from both, right? And so we contribute, and we can contribute to society. And particularly when you have a healthier society that is contributing from women and from all minorities in society that are usually underrepresented, you are empowering this society. And so you are making a huge impact into making it a more developed society, into making it a more impactful one, to raise our children in a better way, to make them aware that you know, there's a contribution from females as much as males in the society. So I think it's really invaluable to us that we have that we should have contribution from women, and particularly in space, because we can all make a difference, and we all think differently. We all have different contributions to make to our universe, and so yeah, I think it's important.
Thanks a lot. وجو كمان عم يتشكرك بالكومنتس. Thank you for your talk. Do you still have any conclusion before finishing and starting the talk around 8 p.m.?
No, I just want to thank you again, Maroon and others who have organized this beautiful event. I was happy to be here to talk to you all. I would be, you know, looking forward for the next time I see you all, either virtually or in person, to talk about science. So yeah, keep looking up, keep being interested in science. And as I said, if anybody has any questions of embarking on an astronomical journey, please feel free to be in contact with me. I was very happy to be here with you today.
Thanks a lot, Dr. Rana. Thank you.
Thank you all.
Bye-bye.
Bye.
Bye. Bye-bye.
Bye-bye.